This is 2.7, part B, on square roots of negative numbers. When I try to take the square root of a negative number, it is not possible to find a real number that works. Because, remember, a square and a square are the opposite. You know that if you had two positives, you would square to a positive, right? We know that 5 squared would give me positive 25. And also negative 5 squared would give me positive 25. It doesn't matter if I'm squaring a negative or if I'm squaring a positive, the result is positive. So it's not possible to take the square root of a negative number and get a real number. What I need to do instead is separate this into this negative 25, separate it into the square root of positive 25 and the square root of negative 1. I can do the square root of positive 25, and that's 5. The square root of negative 1 is defined to be I, an imaginary unit. Okay, square root of negative 1 is considered imaginary. It's not possible to do. I call it I, the imaginary unit. So when I look at any of these examples, for example, square root of 49, I can't do square root of negative 49, but I can do square root of positive 49. Square root of positive 49 is 7, and the square root of the negative is going to be I. Anytime there's a negative number underneath a square root, you can only do the square root if you consider imaginary possibilities, imaginary solutions. The answer to that one is 7I. The next one, negative, square root of negative 81. So I'm going to have negative, the square root of 81 is 9, and then it's negative on the inside, so I'll have negative 9I. The negative coefficient stays, and then my negative inside the radical gives me an imaginary unit I. Okay. The next two aren't going to be perfect squares, so I'm going to have to do some simplifying here. I want to find the smallest perfect square that 20 goes into. 20 goes into 100 5 times, so I'm going to multiply by square root of 5 on top and bottom here. That's going to give me negative the square root of negative 15 over 100. Now there's only one negative here. I have to choose where it goes. We're just going to put the negative with the numerator. So I have negative the square root of 15I over 10. Okay. The I is not underneath the square root. I can't do the square root of 15 or break it down, so I'm just going to leave it this way. Often my math lab actually wants you to drop it off the edge to write it as negative square root of 15 over 10 with the I dropped off of the edge. Same thing, because you can just slide that I off the edge of your fraction. Okay. On paper, they're the same. The next one, let's see, our 54, that's a little bit big. I'm not sure what perfect square 54 goes into, but I do see that my fraction here reduces, so I'm going to start there. I'm going to reduce the 2 into 54. It gives me 1 and 27. Okay. So far, I'm going to have the square root of negative 2 in the numerator and the square root of 27 in the denominator. 27 is also so big that I don't think any of the perfect squares that we had listed in part A are going to work for 27. So if you have a really large number that you're trying to rationalize, you might want to start by seeing if that number can be broken down. So I'm going to write this one as 27 can be broken down into square root of 9 times square root of 3. So I've got square root of 2. How about I just write my I next to it? Just do the negative portion. And then the denominator square root of 9 is 3, and I have square root of 3 left. If I simplify the 27, then I only need to rationalize the square root of 3 piece. So 3 goes into 9, so I can multiply by square root of 3 on top and bottom to get the denominator to have a square root of 9. So I'm going to have square root of the two square root values multiplied together, so square root of 6. I'm sorry, I made a mistake again. Let me go ahead and fix this real quick. Sorry about that. Remember I reduced that? That was supposed to be a 1 now. So it's a 1 now. So I actually just have I on the top. So that's going to be square root of 3 times I. I'm sorry. I knew I reduced that and then I forgot. My denominator, let's see if we get this right. There's a 3 outside times the square root of 9. So I've got square root of 3I in the numerator, and then 3 times the square root of 9 is 3. So 3 times 3 is 9 in the denominator. So square root of 3 times I, all divided by 9. Okay, I hope that made sense. Imaginary numbers are numbers of the form b times I. Actually, all of these numbers that we've seen are of that form, b times I. They're just something times I, whether that something is a 7 or a negative square root of 15 over 10 times I. Okay, that's why my math lab often likes you to swing the I off the edge. You want to write it as square root of 3 over 9I for it to be in imaginary number form. The I should be after the number. Complex numbers are numbers of the form a plus bi, so they have a real component added to an imaginary component. So complex numbers could be something like 4 plus 3i, or 7 minus 2/3 I, or they could have radicals, like it could be 1/9 plus the square root of 15 over 2i. Those are all complex numbers. Now actually, our square root of 3 over 9i is also complex, because you could think about it as 0 plus that imaginary component. So imaginary numbers are a subset of the complex numbers. Complex numbers have something added on to the imaginary piece of the number. The next page, we're going to be dealing with some more complex numbers. We're going to have both the imaginary piece and a real piece. All right, so I'm going to simplify each of these by hand. Some of them will turn out to be complex. Others will just stay real. If they are complex, I want to make sure I write them in their complex form so that I have the a plus bi part separate from each other. Okay. The first one, I've got a square root of 9. The square root of 9 can be done, so this is going to be 3 plus or minus the square root of 9 is 3 over 21. Now, since I don't have any square roots left, I can actually get a value for both the positive and the negative in the numerator. So we're going to separate it and do 3 plus 3 over 21 and 3 minus 3 over 21. We're going to get our two answers. The first one, 3 plus 3 is 6 over 21. Second one, 3 minus 3 is 0 over 21. 6 over 21 can be reduced. Divide them both by 3. That would give me 2/7. 2/7, and the last one can be reduced. 0 divided by anything is 0. So I have two separate real numbers here, 2/7 and 0. The next one is similar, except that they're going to be imaginary because there's a negative value inside the radical. So this one is going to be 3 plus or minus the square root of negative 9 is not just 3, it's but 3i, then over the 24. Now, this one can be reduced because you can divide 3, 3, and 24 all by 3. That would give you 1 plus or minus I over 8. And that is simplified. However, it's not in true complex form. Complex form wants your real part separate. So it's going to be 1/8 plus or minus 1/8 I. And the 1 in the 1/8 I comes from the fact that there is one I here. Don't forget, you need to slide your I off the side of that fraction to be in complex form. Okay. Now, this actually represents two numbers in complex form because of the plus or minus. The two numbers are 1/8 plus 1/8 I and 1/8 minus 1/8 I. Okay. My math lab, of course, will ask you to enter them separately, but together on paper is fine, but they are in true complex form now that I have the coefficients separate from the imaginary piece. Okay. A few more. The next one, the square root of 40, that can be simplified. So I'm going to start with negative 4 plus or minus. I know that the square root of 40 can be simplified because 4 goes into it. 4 is a perfect square. So I'm going to break it into square root of 4 times square root of 10 over 2. So that gives me negative 4 plus or minus the square root of 4 is 2 times the square root of 10 over 2. And then I want to simplify each of my coefficients. So my coefficients are going to give me, let's see, these can all be divided by 2. And if I divide them all by 2, I'm going to have 2, negative 2 in the front, plus or minus the square root of 10 over 1. I don't need to write the over 1 in the denominator. So negative 2 plus or minus square root of 10. Okay. Next, this one is going to give me some kind of complex value because I see a square root of negative 160. I can't do the square root of negative 160, but I know that 16 goes into it, and 16 is a perfect square. So I have negative 4 plus or minus the square root of 16 times the square root of 10. Just go ahead and write your I at the end. You know that you're going to have an imaginary value because you see the negative, so just go ahead and write the I after your square roots over my 2. Okay, so I've got negative 4 plus or minus the square root of 16 is 4, so I have 4 times the square root of 10, and I over 2, divide them both by 2, everything by 2, top and bottom, all 3 coefficients. It gets me negative 2 plus or minus 2 square root of 10 I. The last 2. Okay, I've got another real one, another imaginary one on this side. So the real, I've got the square root of 1200. I might not get the perfect square, but the biggest perfect square in the first try, but I am going to write this as negative 8 plus or minus. I see 100 goes into that. So I'm going to write this as square root of 100 times square root of 12 over 40. Okay, so I've got negative 8 plus and minus. The square root of 100 is 10, and square root of 12 over 40. At this point, I might notice that I can break this down further because square root of 12 has a perfect square, namely 4, that goes into it. Okay, so I'm going to reduce as I do this. I can divide each of these by 2, so it's going to give me negative 4 plus or minus 5, and break down your square root of 12 to square root of 4 square root of 3 over, I'm dividing by 2, so 20. Okay, so continue. You've got your negative 4 plus or minus 5 times the square root of 4 is 2 times the square root of 3 over 20. That's negative 4 plus or minus. You can do 5 times 2 is 10, square root of 3 over 20. And once again, I can reduce because 4, 10, and 20 can all be divided by 2. So I'm going to have negative 2 plus or minus 5, square root of 3 over 10. If you wanted to write this as 2 separate fractions, you could, because the second one would reduce. It may be beneficial in some cases. So in 2 separate fractions, this would be negative 2/10. That one's going to reduce as well, but negative 2/10 plus and minus 5 square root of 3 over 10. The first one is going to reduce to negative 1/5. Divide those both by 2. Plus and minus, you can divide the second fraction by 5, and that gives you square root of 3 over 2. Again, just a different form. It's not any more reduced than the first one. It's just the first one is a single fraction. The second one is a sum or difference of 2 fractions. Last one. This last one is going to give me an imaginary value because I have a negative inside the square root. It's going to be negative 4 plus or minus 128 can be broken down into 64 goes into that, I think. So it's going to be square root of 64 square root of 2. Don't forget the I in the end because you had a negative inside your radical. So the negative inside the radical immediately translates to an imaginary component divided by 20. Then I have negative 4 plus or minus the square root of 64 is 8. So I have 8 square root of 2I over 20. We can divide these all by 4 to reduce. So negative 4 plus or minus 2 square root of 2I over 5. And then because this one is complex, even though the individual fractions won't reduce, it's not in true complex form as one fraction, I must separate it. So negative 1/5 plus or minus 2 square root of 2I over 5, but slide your I off the edge to make it in true complex form. That's the end of section B.